Today's expert, Dr. Thote GHRCE, Supervisor, Dr. Manoj Daigavane, Dean R&D, Dr. Uday Wankhede, HOD, Electrical Engineering Department, Dr. Prema Daigavane, faculty members, dear students, good morning to all of you. I, Shubhangi Giripunje, Associate Dean R&D, feel privileged to welcome you all for the PhD pre-submission seminar of 3 research scholars of Electrical Engineering Department. First is Pankaj Thote. The title of the PhD is Use of Hybrid Intelligence for Smart Protection of Transformer. Second scholar is Shilpa Shravane. The title is Hybrid Intelligence Approach for Optimal Reactive Power Dispatch. Welcome you, sir. I request Pankaj Thote to deliver the PhD pre-submission seminar.
Thank you, ma'am. Good morning, all of you. Respected experts, sir. Respected head of department. Respected supervisor, sir. Respected dean, sir. All the respected professors and my dear friends. The topic of my research is use of hybrid intelligence for smart protection of transformer under the guidance of Dr. Daigavane, sir. The contents of my presentation: objective of research, protection system of transformer, differential relay model for single phase and 3-phase transformer, then differential relay model of a custom built laboratory transformer, investigations on shortcomings of differential protection, use of Wavelet transform for feature extraction and design of an optimal classifier in hybrid sense, statistical analysis, proposed algorithm, performance and DSP implementation of the algorithm, and finally the conclusion. The main objective of transformer protection is to provide the ability to detect internal transformer faults with high sensitivity along with a high degree of immunity to operation on system conditions for which tripping of the transformer is not required. The objectives of my research: first objective is to design the differential relay model of a single phase and 3-phase transformer in MATLAB Simulink environment and to analyze its various operating conditions. To design, build and test the performance of differential relay of a single phase laboratory custom built transformer and to analyze its various operating conditions. Next objective, to explore the Wavelet transforms for feature extraction. Next objective, to develop a novel hybrid k-nearest neighbor genetic algorithm classifier to classify faulted and non-faulted conditions in transformer. Next objective, to train and test the proposed algorithm for the data obtained on single phase and 3-phase transformer in MATLAB Simulink as well as for data obtained on laboratory transformer. Next objective is to compare the performance of proposed algorithm with other classifiers like artificial neural network support vector machine. And final objective is to implement the proposed algorithm on a hardware platform using DSP TMS 320C613T for real world applications. Transformer is a vital and expensive component of electrical power system and hence it needs adequate protection. Protection of a power system is a challenging issue for a protection engineer. For providing protection to transformer for internal faults, the differential scheme is being used where the faults are detected by comparing the currents flowing in and out of the transformer. In differential, mainly we have 2 circuits, differential and the restraining or the stabilizing circuits. The factors affecting differential protection: there are certain abnormal conditions like magnetizing inrush at the time of switching, or when there is a removal of an external fault, or called as recovery inrush, or when 2 transformers they are operating in parallel. When one of the transformers is switched in, we experience an inrush in already charged transformer called as sympathetic inrush, or we may have a condition of steady state overfluxing. For transformers, we have different voltage levels on 2 sides and hence we need CTs of different ratios with different characteristics. Hence we introduce some spill current in differential. Also we have to take care about the phase shift in star delta connected banks. To provide through fault stability, usually we use percentage or bias differential relay. We may have a single slope or dual slope characteristics. As the differential relay operates if the differential current is more than the restraining or bias current. I have prepared differential relay model in MATLAB Simulink environment for single phase and 3-phase, and I also prepared a hardware model for single phase case. First of all, let us see differential relay model for a single phase transformer. I have taken 2 kVA, 230 volt by 230 volt 50 Hz transformer. This is the supply and this is the load. This breaker is used to simulate the charging of transformer, means thereby we can simulate the magnetizing inrush conditions. I have used CTs on two sides to scale down the current. Many of the earlier researchers, they have simply used gain block to scale down the current, but I have used saturating transformer of Sim power system toolbox to scale down the current. Since the rated current is 8.6, I have used CT of ratio 10/1. It is connected in a differential manner to form a differential current. This subsystem block consists of, it has three inputs: differential current, CT output on winding one side, CT output on winding two sides. Again, this subsystem consists of this subsystem, which basically realizes the percentage bias differential relay with harmonic resistance feature. Like, first of all, we have a differential value of current. This function block evaluates the returning current. The returning current is given by some fixed pickup plus bias into the average returning current, means bias into ID1 plus ID2 by 2. Here it is checked whether the operating current is more or less than a differential current. There are certain abnormal conditions like the magnetizing inrush or steady state overfluxing. During that condition, the differential current may exceed the returning current, but that is not a fault conditions. And conventionally, the magnetizing inrush current is identified on the basis of second harmonic content, and steady state overfluxing is identified on the basis of fifth harmonic content. That's why this block calculates the fundamental component of differential, this second harmonic. Here the ratio of second harmonic to fundamental is being taken and it is compared with some standard set limit. This block calculates the fifth harmonic component, and here again the ratio of fundamental to fifth harmonic is being taken and it is compared with certain limit. Let us consider, suppose we have the fault conditions. In that, definitely the differential is more than returning, but the ratio is not above the set limit. Here we will have logic 1 since operating is more than the returning. Since the ratio is not more than the set limit, we will have a logic 0. Not of 0 is 1. Again the fifth harmonic is not significant, we will have a logic 1. Not of 0 is 1. In this case, the input to this AND is 1, 1, 1. Means relay will issue a trip signal because it is internal fault condition. Let us consider a case of inrush. In that, we will have a differential more than the returning, we will have logic 1, but the ratio exceeds the limit, we will have logic 1 here. After not, we will have a logic 0. Fifth harmonic is, if it is not significant, we will have a logic 0 and 1. These inputs are 1, 0, 1. 1, 0, 1, output is no trip. Means although the operating is more than the returning, the relay will not issue a trip because second harmonic resistance will come into picture. Similarly is the case for overfluxing conditions. Here the output is taken as trip, which is the output of this subsystem. Ultimately this is taken as output here, which we can observe on the scope. Now the validation of Simulink model. First of all, the waveforms of the load current on two sides. Since voltages are same, 230 and 230 on two sides, the rated current 2000 divided by 230, something 8.6, peak root 2 of 8.6 around 12 ampere on two sides. These currents are correct. Then the behavior of current transformers. Since I use the CT of ratio 10/1, it will scale down the current by a factor of 10. 12 divided by 10, something around 1.2 with 180 degree phase shift. The CT currents on the two sides, they are nearly same in magnitude and same in phase shift, so that differential current is nearly 0. This modeling of CT is correct. In the simulation results, means relay output for various conditions. First say loaded condition. For normal operating conditions, the operating is well below returning, relay will not issue a trip signal. For internal fault conditions, operating current is more than returning and relay will immediately issue a trip signal. Differential relay should provide through fault stability. It should not operate for a fault outside the CT location for external fault. For external fault, it automatically adopts its pickup, and for external fault, the operating is well below returning and the relay will not issue a trip signal. Magnetizing inrush condition. At the time of switching off an unloaded transformer, due to flux doubling effect, which depends upon the point on way of switching, transformer core enters into a deep saturation. Its inductance and reactance becomes extremely zero, and hence it draws the asymmetric peaky waveform from the supply called as the inrush current. The peak of this inrush is reported to be 8 to 30 times of the full load current, and this peak will hit the differential protection. The response of the developed model for this inrush condition. For this inrush, definitely the operating is more than restraining, but still relay is not issuing trip signal because second harmonic restraint will come into picture and relay will not issue a trip signal. Condition for switching with in-return fault, again operating is more than restraining, the relay will immediately issue trip signal. Overfluxing condition, steady state overfluxing, which mainly happens for a generator unit transformer where if V by F ratio exceeds the nominal limit of 1.1. Here again, though the operating is more than restraining, the fifth harmonic restraint will come into picture and relay will not issue any trip signal. Thus, for all the operating conditions, the developed differential relay model operates properly. Hence, the developed model can be used for the data acquisition. Here I have taken data for one frequency cycle, means 20 milliseconds, at a sampling rate of 10 kilohertz. This table explains the data. Like I have captured internal fault data 454 with various types of fault, like internal fault on primary and secondary side with percentage of shorted turns. Then internal fault on primary secondary at the time of switching with various switching instant with various percentage of turn shorted. Total data is 454. Data of other disturbances. In that, first of all, I have taken data of the inrush current for various switching instants. At that time, the SHR was more than the set limit of 20%. Now the point is, in modern day power transformers, due to improvement in the core material with a view to reduce core losses, the amount of second harmonics, they are reported to be very less, even less than 7%. That's why differential relay based on harmonic restraint maloperates. I also want data of inrush so that SHR is less. For that, what I have done is, in my simulation, I have adjusted the BH curve and thereby I have taken the data of inrush with various switching instants. I have also taken overfluxing condition with different V by F ratios. Total data is 676, out of which I have used only 25% for training, and I will check the performance of proposed algorithm for new 75% eventualities. Then moving ahead, then I have developed the model for a three-phase transformer. There I used 25 kV 11 by 0.4 kV delta star transformer. This source indicates basically supply from grid. This is a load. The HV side is in delta and LV side is in star. This delta star connection will introduce a phase shift of 30 degree. To compensate for that phase shift, I have used CTs on the two sides to scale down the current. To compensate for the phase shift, the CTs on delta side, they are connected in star manner, and CTs on star side, they are connected in delta manner so as to take care of 30 degree phase shift. Again, there are for 3 lines, the differential circuits are formed. The subsystem consists of these 3 subsystems for 3 lines. For each of these subsystems, the inputs are the differential current and the CT output for winding 1 and winding 2. Again, for each of these subsystems consists of the bias percentage differential relay with harmonic restraint feature, as I explained for earlier case. Like we have trip output here for the 3 lines. If the trip output is high for any one of the lines, then I use OR block. The relay should operate, means priority must be given to the operating current. Then the CT calculations, my HV current is 1.312, that's why CT ratio is 2:1 is selected. LV current is 36.08, but CTs are taken in delta manner, means the is 62.49, the ratio is taken as 100:1. Means on HV side, current is scaled down by factor of 2, it is 0.656, which will be flowing over here. And on LV side, it is 6.624 ampere, which will be flowing over here. The difference is 0.032 unbalanced current. Usually the pickup is taken as 5% of the output CT current. Output CT current is 1 ampere. 5% of 1 ampere, 0.05, which is more than the 0.032. Then validation of Simulink model. First of all, the waveforms of the load currents. On LV side, 1.3 is √2. On HV side, on LV side, 36 is √2. The currents are correct, √2 times. The performance of the CTs on HV side. On HV side, the CT scales down current by factor of 2. Means current gets scaled down by factor of 2 for all the 3 lines. On LV side, it scales down by factor of 100 for all the 3 lines. Then, the instantaneous current on the output side of CT on HV and LV. This red indicates the output CT for LV and black HV. The two waveforms they superimpose on each other. Means the output CT currents on HV and LV, they are nearly same in magnitude and same in phase shift, so that differential current during normal condition is near to zero for all the three lines. Means performance of CT is correct. Then simulation results for various operating conditions. For loaded conditions, the operating is above restraining, relay will not issue a trip signal. For internal fault, any one of the internal fault, like if operating is more for any one of the lines, like in this case it is more for two lines, relay will issue a trip signal. External fault, it is providing through fault stability. The operating is well below restraining and relay will not issue a trip signal. Then inrush current, waveform inrush current. For magnetizing inrush, operating is above restraining, but relay is not issuing a trip signal based on second harmonic restraint feature. Overfluxing, if E by F ratio exceeds limit, although operating is more than restraining, relay is not issued trip signal. Switching with internal fault means if there is an internal fault at the time of switching, this is a very rare possibility. There, first for initial some time, the relay is not issuing a trip signal as long as the inrush dies out. Then relay issues a trip signal. Thus, a developed model responds correctly for all the operating condition and hence it can be used for data acquisition. Here I have collected data again for one cycle, and in differential I am taking decision based on the data of three phases. Means I will have data of three phases. This table shows the data like for internal fault, I have performed a terminal fault on LV sides with various percentage of loading and with various fault resistances, with various switching instance. Then again the magnetizing current with various switching instance and with various residual fluxes for the three phases. And again I have collected data of inrush by modifying the GHRCE so that SHR is less than 20%. My point is that my proposed algorithm should work correctly in spite of the amount of harmonic contents in the inrush. I have taken data of overfluxing, total 11 values, total data is 4040, out of which I have used only 30% for training and 70% for testing. In moving ahead, I also developed a model, laboratory model for single phase case. I use 2 kV 230 volt by 230 tap transformers. Means with this we can short circuit the 10% and 20% of turns on winding 1 and winding 2. The CTs they are used as 10 by 1 ampere 10 VA with 5P10 protection class. They are connected in a differential manner to form a differential circuit. Here I have used 3 resistors, each of value 3 ohm of 5 watt each in parallel, so that the effective resistance is 1 ohm and this is a load. Then we can observe the waveform of the differential on this DSO. This is a photograph of a custom built 2 kV transformer, the tappings to perform internal fault. Photograph of a 10 by 1 ampere 10 VA CTs to scale down the currents with the accuracy class of 5P10. 3 resistors that have been parallel to form a differential resistance of 1 ohm. This is a photograph of a complete experimental setup for capturing data. This is a 2 kV transformer to be protected, 2 CTs collected in a differential manner, and this waveform can be observed on this DSO. From supply we can have random switching to record the inrush. Sample waveforms of the DSO. For normal condition, the differential current is near to 0. The sample waveform of inrush for any one of the switching. This is a waveform of fault during switching. This is a waveform during interturn fault condition. Waveform during recovery inrush means I have cleared the external fault, and as soon as the external fault is removed, the voltage is increased and an inrush is observed called as the recovery inrush. Data acquisition, data for one cycle is taken, like the internal fault data is 52, internal fault on primary and secondary with various percentage shorted terms. Then internal fault at a time of switching with random switching instance. For magnetizing, the data of inrush for various random switching, there we cannot control the switching instance, random switching. Then the data of inrush I have modified by adding certain frequency component so that SHR is less. Every time my focus is to acquire data of inrush so that SHR is less. Then the recovery inrush by randomly clearing the external faults. The data of sympathetic inrush means 2 transformers operating in parallel. When one transformer is switched in, there is an inrush in already energized transformer called as sympathetic inrush. Total data is 207, out of which 30 decimal data is taken for training and 61 is taken for testing. Then thus I have data for various transformers. Then investigations on shortcomings of differential protection. Conventionally, the percentage bias differential relay with harmonic resistance feature is used for identifying the abnormal conditions like inrush and overfluxing. But in new power transformers with new core material in view to reduce core losses, the amount of second harmonics they are less. Also during fault condition when CT saturates or when a EHVAC line is terminated by a transformer due to the capacitance of a long EHVAC lines, the amount of second harmonics in internal fault they are recorded to be more than the state limits. These shortcomings creates the scope for development of new algorithm which basically aims at wave shape recognition based technique for accurate and rapid discrimination between faulty and non-faulty conditions. Then I have used wavelet transform for the feature extraction. Conventionally we use Fourier transform to find out the frequency content, but signals in hand should be stationary. If the signals they are transient, they are non-stationary having different frequency components, earlier short-term Fourier transform was used, but it suffers the drawback of windowing. That's why wavelet transform is used, because it gives information both in time domain and frequency domain. This is the implementation of DWT. The signal in hand is decomposed into two parts: high pass filter, low pass filter, detail and approximate. And again these signals can be decomposed further up to desired level. Like in this research I have used Dobeshik 6 as a mother wavelet and the signal is decomposed up to level 4. This is a sample waveform of the differential current. These are the coefficients, current coefficient at detail 1 level, 2, 3, 4 and the approximate 4. For a sample case when the sampling frequency is 10 kHz, detail 1 consists of the frequency band 2.5 to 5, detail 2 1.25 to 2.5. At every level the frequency is half as per Nyquist sampling theorem. Then the statistical analysis of DWT coefficients. After studying these DWT coefficients during inrush condition and fault conditions, I have collected, after rigorous analysis, I have collected certain statistical features like kurtosis, variance, energy of level 1, mean absolute deviation of level 2, kurtosis of level 3, maximum of absolute value, mean absolute deviation of, this is for D4, this is for A4, and kurtosis of level C4. I also prepared some scatter plots to see the variations. For a laboratory transformer case, this is the kurtosis of level D1, this black indicates inrush and this red indicates fault. Then variance of level D1, energy of level D1, mean absolute deviation of level D2, kurtosis of level D3, maximum absolute value of level D4, mean absolute deviation of level C4, and finally kurtosis of level C4. If we observe these 8 scatter plots for 8 operating conditions, we have some conclusions like the data is not linearly separable. Any single parameter is not sufficient for classification. Hence all the statistical features they are combined to form a feature vector, because the merit of any classifier depends upon the input which it gets for the classification. Proposed algorithm. Basically I use k nearest neighbor simple rule of data mining. It is an instance based learning method. All distances corresponds to points in n dimensional Euclidean space. In my case total features are 8, means 8 dimensional space, and classification is done by comparing feature vectors of the different points. Suppose for sample case, like we have data, this black indicates suppose fault condition and this indicates inrush condition, and whenever a new testing sample comes, it searches for its nearest neighbor, and I have searched the nearest neighbor using 4 types of distances of statistics: Euclidean, city block, correlation. I will explain there. I use a very simple concept of GA. There are 4 attributes of GA like evaluation, selection, crosshair, mutation. I have taken only crosshair operator of GA. Like I am searching the nearest neighbor using Euclidean, city block, cosine, correlation, distance. Then like suppose we have 4 types of distance. By distance first, the nearest index is fault. By distance second, the nearest index is fault. By distance 3, nearest index is fault. By distance 4, nearest index is inrush. Then maximum GS, fittest should survive. Then the maximum time the decision is fault, that will be categorized as a fault. This is a flowchart of proposed algorithm. First of all, we will have the offline training of relay using statistical parameters. Then sample of differential current in the case when operating is more than listening. If operating is less than listening, we need not to bother. Then normalization and wavelet decomposition, formation of feature vector using those 8 statistical features. Then use of hybrid k-nearest and genetic algorithm for classification. If that sample is fault, relay should issue trip. If it is not fault, process next sample of differential current. And here a decision is taken based on the data of 1 cycle. Performance of the proposed algorithm. This is sample waveform captured on laboratory DSO. This is an instance of switching. We have an inrush current. Then it dies out depending upon the time constant. And then at this instance I have performed a fault. Here I have taken fixed threshold condition. For first 3 cycles, the operating is more than the pickup, but this is not fault. The algorithm should not give a trip signal. Here it is less. And here as soon as we have fault, it should be diagnosed as a fault. Then as per the working of this algorithm, I have displayed some messages if the category is fault or inrush. For first 3 cycles, that is categorized non-fault. Means I have displayed the message, do not issue trip signal. For here, process next samples because operating is less than listening. And as soon as we have fault, issue a trip signal. Means the proposed algorithm responds correctly for the differential current. Then the performance of the developed algorithm for data opted on various cases. Case 1, MATLAB Simulink model single phase, total conditions are 507. Proposed algorithm gives accuracy of 96.64%, whereas the support vector machine gives accuracy of 92.89% and ANN with back forward feed proportion network accuracy of 94.67%. Then for a 3-phase transformer, proposed algorithm gives accuracy of 96.92%, ANN 91.19%, whereas the SVM train instruction of MATLAB was unable to optimize a large data set. Then for a data on single phase transformer laboratory, SVM gives accuracy 94.16, ANN 94.89, proposed algorithm gives increased accuracy of 99.27. For all the 3 cases, the proposed algorithm gives better accuracy. Then I have calculated the average performance for all the data. SVM gives accuracy of 93.02, ANN 91.82, and proposed hybrid KNGA gives an overall accuracy of 96.97% as indicated by this bar diagram. I have also compared the performance of proposed algorithm with conventional harmonic restraint scheme. Say for a case of data on laboratory transformer. For a data set of 138, the harmonic restraint method responds incorrectly for 31 cases, giving an classification accuracy of 77.53%. Whereas the proposed algorithm, out of 138, 137 times it responds correctly, giving an accuracy of 99.27%. Thus, proposed algorithm is also superior as compared to conventional harmonic restraint scheme. Then finally, to have a real world application, I have implemented the proposed algorithm on a DSP platform. For that, I have used TMS 32066-713 DSK kit. It has got 4 audio ports and 4 inputs and 4 output LEDs. This is a integration of a math work with the Texas DSP tool. This is the photo of a DSP kit connected to the MATLAB. It has got 4 input switches, means at a time we can test 16 type of possibilities on this DSP kit. 4 output LEDs are there, out of which first LED has been configured for non-fault condition and second LED is configured for fault conditions. The DSP responds properly for my algorithm. Finally, the conclusion of my research. In this research work, a novel hybrid KNN-GA based differential protection scheme is proposed, which effectively differentiates internal fault with the other type of disturbances in the transformer. Performance of the proposed algorithm has been tested extensively and the following conclusions are made. A wide range of tests has been performed for the proposed scheme on a MATLAB Simulink model as well as for a laboratory custom built transformer. The results are encouraging. The performance of the proposed scheme has been checked for different transient states such as magnetizing inrush or excitation. The proposed algorithm relay operates correctly and it remains stable for all the cases. The proposed scheme has been tested for fault both inside and outside the protected zone and correct responses are obtained. The proposed scheme operates reliably for different turn to turn and turn to ground fault. The performance of the proposed algorithm has been compared with the classifiers used by previous researchers and accuracy of classifications found to be increased. The proposed scheme also has been implemented on DSP board TI-TMS 32066713 DSK to check its performance in real-time operation. My publication, 2 of my papers are under review at SCI Index Journal. One is at Canadian Journal of Electrical and Computer Engineering, another is at Modern Power Systems and Clean Energy. I have published my 3 papers in international journals. I have presented 2 papers in international conferences. The paper of this 7th International Conference on Emerging Trends in Indian Technology is soon going to be published in IEEE Explore. I also presented my paper at MNIT Jaipur. These are the references which I have used during my research work. Thank you, sir.
So basically what you are trying to do is that to separate out the internal faults, right, signature with that of the magnetizing inrush current and others, right. So, and in doing so, if I have correctly understood that you have looked into only the second order harmonics that are present, right. So if second order harmonic currents are present, so you will not consider that as a fault, right. So, but the thing is that suppose this internal fault is such that it may also generate a second order harmonic signature. So in that case, what will be your...
Right, sir. My algorithm is not taking decision based on second harmonic. If
So can you explain that, because you have only presented the results, but
Right.
what is underlying it?
Yes,
what
sir.
is the basis of it? You have not discussed in detail. So can you just elaborate on that point?
like sir, is first of all I have done the decomposition of my signal using wavelet. We have wavelet, it's statistical parameters of wavelet coefficients. Like we have wavelet coefficient of detail 1, detail 2, detail 3, detail 4 and approximate 4. Whatever these wavelet coefficients are collected, then I have taken certain statistical parameters of those wavelet coefficients like kurtosis, mean, standard deviation, etc.
But that is actually missing in your thesis, right? Those analyses, that rigor is missing. So can you include those on? This is how you are actually, because the thing is that you have shown through your results, your simulation that it is happening. But people would like to know that what is the basis of the algorithms that you have used, right? Or the mathematical analysis. So that part is missing, right? So there you have to actually see in your simulation as well as in your experimental results. You can actually you have shown that these internal faults are being differentiated, but there may be cases that where these internal faults may also have some second order harmonics, and then what is the effect of coupling between the two, right? Where your algorithm will fail. So that you will be able to appreciate, or one can appreciate only if you present a rigorous analysis being presented.
Yes, sir. I have, that's why deliberately I have the data set of inrush where second harmonic is less, and I have a data set of fault where second harmonic is more. I am not taking decision based on second harmonic. That where my research focuses. For that, what I have done is I have done the wavelet decomposition of the currents during various conditions, and I have collected its statistical features, and those statistical using those statistical features, I am taking a decision.
Okay, fine. Carry on. Then, see, my only thing is that you have only presented the results,
Okay, sir.
right? Right? So that is an analysis, right? So because ultimately, what you are doing is nothing but nothing more than that of a signal processing.
Right.
Right? You are taking the signal and you are understanding its signature.
Right.
So that, in order to understand the signature of the signal that you have captured, right? So you have to do some analysis before you come to a conclusion. You have shown the conclusions, you have shown the results, but that how you have come to that level, up to that level, so that part is missing. Right? Are you getting what I am saying?
Right, sir.
So the signal processing part
Right, sir.
is missing in the thesis.
Sir, that is the summary copy. In thesis copy, I have included everything.
Okay.
This
No,
is
this is not
summary
summary.
copy, sir.
Okay. But in the presentation also it is not there, so that's why. Right? Second thing, see, you have given all the results in form of this actual absolute value of current, but it will be because it would be nice that if you present it in form of power units, because that will give you the feeling that at what power level you are operating, what is the this level of fault current that you are considering, as well as this inrush current, right? So one thing, see, in order to make it more poignant, so what you should do is that actually the thing is that you take several cases of magnetic inrush currents, right? Which is you have taken only one or two cases of magnetic inrush currents.
No, for various random switchings, I take 101 somewhere.
So not the instead of switching, but the magnitude of the this inrush current also will affect. If there is a say, if the magnitude is less. Right? When the magnitude is higher, then the differentiation becomes easier to do.
Right.
When the magnitudes are of similar levels, then it becomes difficult. So you take those difficult cases and try to try to show that actually this algorithm works.
Sir, I have taken like total around
3,800
for 3,800 cases.
I'm asking, though, there is no point of taking so many cases. Only those cases where these levels are too close to each other.
Right, sir. Like you are saying, the peak of the inrush. It depends on the instance of switching. Like if instance of switching is near to 90 degree, the peak is very less. That cases also I have incorporated in my study.
And second thing, that how you are actually determining the second order harmonics in the signal. So you have got only the raw signal. From that raw signal, how you are decomposing it into the second order harmonics and the other harmonics.
So I have used the ready-made block available in MATLAB, second harmonic, to find out second harmonic content of signal.
But that may not actually in actual system, how you do that?
For that we have filters.
But filters will introduce delays.
Right.
All those problems will come up.
But in numerical relays,
so basically, see, ultimately what you are actually working on is towards the numerical
relays.
So the whole issue is that how you are decomposing the signals and how you are processing the signal.
Right, sir.
So your main emphasis, although the results are fine, but then your main emphasis should be that the signal processing part of it you should give more importance to the signal processing part of it. Otherwise, these people will keep on asking these questions. Right. So this then the second part, the delay that you have used only for this optimization purpose or anything else?
Using 4 types of distances, I am searching for the nearest neighbor. That attribute I am including, crossover operator of G simple.
No, so my question will be, or my objection, let us say, just to have that debate. See, this generally we use GA or this artificial and in those cases where the mathematical model is not known.
Right.
But here the mathematical model as well as everything is deterministic.
Right.
Everything is known.
Right.
So still why you are using GA? So that question will come up. So what will be your answer to that?
Like my simple concept is fittest should survive. Like by 4 types of distances, I am searching the nearest neighbor. By 3 types of distances, if category is classified as fault, and by 4 type of distances. If category is classified as inrush, the distance should be fault.
Yeah, so but if I know the model of the system, that if I know the differential equation of the system perfectly, then I can do it without going without testing all these 4 conditions. Right? So generally these GAs are being used on those systems where the mathematical model is not available readily. Right? So you have to form a proper justification that why you are using that. Right? I think that is fine. Right. So you because only part what is missing in the summary what is given to you is that is really lacking is that analysis part of it, signal processing part of it. So that because the whole of your numerical relay is actually based on that these experiments and simulation. Yes, fine, it has got value, but then ultimately people would like to know that how you have done that analysis. That's all there is.